and I'll be going through Team A4's ultrasonic and accelerometer module. So my team consists of Tianwei, Christabel, and me. So yeah, I'll be going through more on the ultrasonic side as well as a bit on the accelerometer system design. So we made certain improvements to the ultrasonic responsiveness. So for our ultrasonic and accelerometer module, we are using timer 32 as a free running mode to create an accurate delay using an interrupt service routine instead of using a follow-up delay, which might not be very accurate, right? So as you can see here in this code, we created a function. So this function takes in an input of how long you want to delay, right? So we first set the global delay flag to false. So we are using a function to calculate how much to input into the timer 32 register. So for example, if we put 3000 ticks in the timer, into the timer register, there will be a delay of 1 millisecond. So when we start the timer over here, um, the timer will be inputted with the register value calculated, and then it will run down, right? So when it runs down, it will set the delay flag to true. So when the delay flag is set to true, this blocking thing will be undone, and then the timer will be halted. So finally the interrupt has occurred, and we are out of this delay. So this is how we implemented the delay, which is more accurate than using the follow-up delay. So we also use the 20 filtered values instead of one value for our ultrasonic sensor to obtain a more accurate and consistent reading from the ultrasonic sensor. So this came where we had certain problems where our readings weren't that accurate. We were getting certain anomalies in our readings. So instead what we did was every time, let's say, a mapping team calls our function to get the distance, we will use a average of over 20 values. So we will like get 20 values instead of just one value. So yeah, so my teammate will be explaining more on that during the filter part. So yeah, moving on. So here are some of the codes. So for here, in this case, we created a struct called ultrasonic sensor configuration. So this contains a configuration for each sensor. So for example, which trigger port is it in, which trigger pin, echo pin, which timer is it using, which global interrupt count is it using, and where do we store our values. So we created a global buffer array to store the latest ultrasonic values. Okay, moving on. So you can see here in this trigger ultrasonic sensor, we are taking this struct as an input, a pointer to this struct as an input. So we are using this struct, so we destructure this struct, the trigger port, the trigger pin. So we are setting GPIO high on this trigger port and trigger pin that's provided by this struct. This will set output high and send it to send a pulse, create a pulse. So we'll create a 1 millisecond pulse, which is more than the 20 microseconds stated by the MP SR04 datasheet. And we finally set the output low. So this will send create a pulse and basically let the ultrasonic sensor know that okay, you have to start taking a reading now. So we also created this function which is to get distance. So this is actually the main function of the code to get the distance from the ultrasonic sensor. So as you can see here, we first triggered the ultrasonic sensor. So after sending the pulse to the echo pin, to the trigger pin, we'll wait for a positive edge from the sensor. So for the sensor to send back its first reading, right? So it's polling. So yeah, we are using polling for this, and we'll finally we'll reset the global interrupt count. So after that we'll set a timer to start. So after that we'll wait until the ultrasonic sensor has finished sending its last value into the echo pin. So there'll be another blocking thing here, and then we'll finally stop the timer. So after that we'll finally get the duration using the values in the timer register, and the global interrupt count. So as you can see here, there's this get duration which is used to get the total time elapsed. So as you can see, there's a pulse time. So this is found by the global interrupt count multiplied by the timer A tick period, which is 1000 if I'm not wrong. So this is actually a 1 second timer. So we have another one which 1 millisecond timer. Sorry, we have another timer A get counter value, and this will get the add back the remaining value found in the register, and finally we'll clear the timer. So this will return the total time elapsed. And yeah, so this is how we get the duration. And finally we'll divide by 58.0f, which is stated by the datasheet, to get the distance. Yeah, so this is our interrupt handler, a very small one, just to increment the global interrupt count. So moving on, I'll be talking more about the accelerometer and basically the system, the software design behind it. Sorry. So we actually use I2C for communication between MSP 432 and MPU 6050. So this is directly linked using the SDA and SCL ports, which are 6.4 and 6.5 on the MSP 432 respectively. So we are using this UCB1 base, which is what was specified in the MSP datasheet. So as you can see here in this diagram, we created a diagram. We took this diagram online that explains a bit about I2C. So we first send a start condition, which is SDA goes down and SCL goes down after that. And then we'll send the address to read or write from. So these are the 7-bit address to read or write from. Yeah. So this is a read or write operation, and this will send a command to read or write, and then data will be transferred over SDA. Yeah. So now I'll be passing the time over to. Oh, sorry, still one slide. So yeah, so we have the software designed for the harm detection. So yeah, so here are the addresses that we found from the datasheet. So we have the slave address here, which is how the MPU 6050 connects with other microcontrollers. So this was stated in the datasheet. So it's 0x60. So what we did was we specified this slave address in the I2C config when we first start the program in our main function. So we have a reset address. So it's 0x60. So when we write 0x00 to 0x6b, it triggers power management 1, which resets MPU 6050's power settings. So basically this allows us to set the accelerometer to a clean slate. So everything will be everything will be good because it's a clean slate, so that it'll be easier to debug. We also have the other three functions here. Sorry, the other three addresses. So we have the accelerometer address, gyroscope address, as well as the temperature address. So the accelerometer address has 6 bytes of data, and gyroscope address has 6 bytes, and temperature has 2 bytes. So these are how we got the values. So we use our I2C read or write functions to access these values. Yeah, so now I'll be moving on. I'll be passing the time over to Tianwei, which he'll explain more on the recalibration and filters.
Thank you, there, Kevin. This is Jian Wei. For the recalibration, in order to make the measurements of accelerometer, we use a calibration methods by reading 200 times of all values. Then we will average out the values. As we are holding the sensor in flat still position, the expected output value should be 0. So with the calculated values, we can get the average error of the sensor's mix. So we will offset the error to every output value. This will help our accelerometer filter, which we will explain later. For the harm detection, when the harm is detected, a harm is detected once the gyroscopes measure an angle which exceeds the threshold of 1.5 degree. Then we will start incrementing the global variable until the gyroscopes measure another angle that exceeds the threshold of negative 1.5 degrees. Then we will proceed to calculate the harm height using trigonometry. We use the values of notches received from the encoder team, which we will start the calculation of notches once the harm detected boolean flag turns true. Then the encoder team will return us the distance traveled on the harm once the harm detected boolean turns false. Then we used the distance and the angle measured by the gyroscope by using the trigonometry to calculate the harm height.
So we are recalibrating the MPU 6050. These are the errors. These are the angles being shown, the angle change. Now we'll be showing the car with the accelerometer. Moving up the hump. As you can see, we will now pause the program. We've got a hump height of 1.75 cm and a hump detected.
These are the three filtering methods we are using for our ultrasonic: simple moving average, limit filter, exponential moving average. For simple moving average, it's just the average of all values in the float queue. For limit filter, we cut off all inaccurate values that exceeds the threshold. For exponential moving average, more weight is given to the more recent values encouraging accuracy. We will be using simple moving average together with the limit filter for our ultrasonic values, because we feel that the limit filter is good as we can remove the anomalous value that does not accurately reflect the specification found in the ultrasonic datasheet. We are also using simple moving average to get the average of the float queue to return a more accurate values.
So this is a real life demo of what we did in order to get the filtered graph, as you can see on the slides. Yeah, so I hope Prof, this will get you a better understanding of how we test our different boundary cases and to check whether things when it's within the threshold and outside threshold, what will it look like. This is our team's real life demo of a 7.8 cm. And in the next experiment will be a 15 cm, 15.8 cm, and next it will be talking about when the sensor is facing backwards to the wall and how far it can detect, so about 60 cm. And lastly, when it's out of the threshold, how when it's facing the ceiling and it's definitely more than 200 cm, what will it show? It will show a rough value of 200 cm. So next, we'll be talking about the testing that we did for our accelerometer. So for our accelerometer, we did 3 test cases. One being the valid flat surface detection functionality. So by letting the car run on a flat road, we will check whether the accelerometer will be able to return approximately 0 degrees, and the actual result that we were able to get is really approximately 0 degrees. So secondly, for our valid curve line slope detection functionality, we will let the car run on a curved line slope, and by doing so, we were able to return more than 1.5 degrees. And lastly, we will is the check valid harm detection functionality, where to check if a harm is actually detected if a pitch angle is more than 1.5 degrees. So we were able to test that with a pitch angle of 1.75 degrees, when the actual result was as what we expected to be Boolean detected harm to be set as true.
Play. Recalibrating.
This is our test case 1 of the accelerometer testing, where if the car is going on a flat road, our return estimated value should be approximately 0 degrees. And as you can, this is an example of a real life demo of what it looks like and how it is proven to be true. So thank you, Prof, for your time.